Stop AI agents from dangerous database actions by designing narrow MCP tools, server-side guards, and approval gates. Let's begin with what we are securing. An AI agent becomes risky when it can call tools that change data. In MCP, tools can give a model access to databases, APIs, files, and workflows. That power is useful, but a badly designed tool can create real damage. The safest design starts before the agent sees the tool. In this tutorial, we build a local demo MCP server with safe mock database tools. The goal is to understand how to prevent destructive behavior by design. That sets up the security roadmap. First, we will map how an agent reaches a tool. Then we will identify where database risk appears. Next, we will build a local mock MCP server. After that, we will add read-only tool design, input validation, audit logs, and proposal-only actions. Then we will test a safe request and a blocked destructive request. Finally, we will connect the demo to production-grade security requirements. With the security roadmap in mind, the next piece is how MCP tool risk happens. MCP lets a host discover tools exposed by a server. The agent can decide when a tool is useful for the user request. If the tool is read-only, the impact is usually limited. If the tool can delete, update, or write data, the risk increases immediately. The problem is not MCP itself, the problem is unsafe capability exposure. A secure server exposes the smallest safe capability needed for the task. That idea leads directly to the dangerous anti-pattern. The worst design is a generic database execution tool. A tool like Reviewable gives the agent too much power. Even a helpful model may call the wrong operation if context is confusing. Prompt injection or poison tool metadata can make this worse. Instead of exposing raw database power, expose narrow business-safe tools. The safest delete tool is usually the one you never expose. Once the dangerous anti-pattern is clear, local project setup becomes much easier to understand. The demo starts with a small TypeScript project. We install the MCP SDK and XOD for schema validation. The SRC folder holds the local server and mock data. The .cursor folder holds the project MCP configuration. This is intentionally small so the security ideas are easy to see. The first working version should be local, inspectable, and easy to break safely. From there, the next practical step is minimal package scripts. The package scripts separate development from runtime. Dev runs TypeScript directly while you are building. Build compiles the server into dist. Start runs the compiled server with Node. For stdio MCP servers, a clean runtime process matters. The MCP host should start a predictable compiled file. This sets up the next important point, TypeScript output settings. The TypeScript config controls how the server is compiled. root_dir keeps source files under SRC. out_dir writes runnable JavaScript to dist. Node next supports modern module imports. Strict mode catches simple mistakes early. This matters because the MCP host launches the compiled server file. That sets up fictional mock data. The server needs data to demonstrate database safety. We use fictional customer rows only. There is no live database connection. This lets us test read behavior and blocked requests without risk. The important lesson is the tool boundary, not the data volume. A small fixture is enough to show the security pattern. With fictional mock data in mind, the next piece is define tool policy first. Before writing tool logic, define the policy. Each tool should have a clear effect type. Read tools return data without changing anything. Proposal-only tools prepare a reviewable plan. Approval requirements should be explicit, not guessed from the tool name. This policy becomes the security map for the server. That idea leads directly to guard read-only inputs. A read tool should reject non-read operations early. The guard accepts select style demo inputs. It blocks destructive-looking operations such as delete, drop, update, alter, insert, and truncate. This is only one demo layer, not complete production security. The stronger production pattern is dedicated read APIs and read-only database roles. Still, this guard makes the risk visible in code. Once guard read-only inputs is clear, audit logging becomes much easier to understand. Security needs visibility, not only blocking. Every tool call should leave a trace. The audit helper records tool name, effect, status, and time. For stdio servers, logs should go to stare, not stout. This keeps protocol messages clean while preserving observability. In production, audit logs should be durable and searchable. From there, the next practical step is create the MCP server shell. The server file brings the pieces together. It imports the MCP server class and stdio transport. It imports ZOD for input validation. It imports mock data, read-only guards, and audit logging. At this point, the server has a name but no exposed tools. The next step is to add safe tools only. This sets up the next important point: build the safe read tool. The first tool is intentionally read-only. It accepts a short query string. The guard checks whether the input is safe for this demo. The audit helper records that the call was allowed. The tool returns fictional rows as a demo result. No database mutation is possible through this tool. No database mutation is possible through this tool. That sets up convert risky actions into plans. Some requests sound like they need a change. But the agent should not directly mutate important data. This second tool creates a simulated cleanup plan instead of changing records. It returns a reviewable message. The audit status is approval _ acquired. This pattern turns dangerous action into controlled decision support. With convert risky actions into plans in mind, the next piece is connect over stdio. After tools are registered, the server needs a transport. Stdio lets the MCP host launch the server as a local process. The server receives protocol messages through standard input and output. Errors are written to stdio so protocol output stays clean. This is the connection layer for the local demo. If startup fails, the MCP host will not discover tools. That idea leads directly to project MCP configuration. The project config tells the host how to start the server. The server name is local MCP security demo. The command is node. The argument points to the compiled dist/server.js file. Keeping the config project level limits accidental reuse. After changing server code, rebuild before testing again. Once project MCP configuration is clear, test a safe read request becomes much easier to understand. A good first test should prove the safe path works. The prompt asks the agent to call the mock read tool. The tool receives a select style demo query. The result should show fictional rows only. This verifies discovery, schema validation, guard logic, and tool response. If the agent answers without calling the tool, make the tool requirement explicit. From there, the next practical step is test a blocked destructive request. The second test proves the guardrail works. The prompt uses a destructive-looking input against a mock table. The tool should reject the request before returning any data. The expected result is a blocked operation message. This teaches the viewer to test failure paths, not just happy paths. Security behavior must be verified intentionally. This sets up the next important point: inspect tool discovery. Tool discovery confirms what the host can see. The list command should show the local demo server. The list tools command should show only the safe mock tools. If an unexpected tool appears, treat it as a security problem. If no tools appear, check build output and config path. Security starts with knowing exactly what is exposed. Security starts with knowing exactly what is exposed. That sets up threat 1, too much tool power. The first threat is overly broad tool power. A generic SQL tool is flexible, but dangerous. A narrow read tool is less exciting, but safer. A proposal-only tool is safer than a direct write tool. The question is not, can the agent do it? The question is, should this capability be exposed at all? With threat 1, too much tool power in mind, the next piece is threat 2, prompt injection. Prompt injection can arrive through user text, documents, tool outputs, or metadata. The model may see text that tries to override instructions. A database tool should not trust natural language as permission. Permission must be enforced in code, outside the model's judgment. That is why schema validation and server-side policy matter. The model can request, the server must decide. That idea leads directly to threat 3, tool poisoning. Tool poisoning means malicious instructions can be hidden in tool descriptions, schemas, or outputs. The agent may treat that text as instruction instead of metadata. Do not connect unknown MCP servers casually. Review tool names, descriptions, schemas, and outputs before trusting them. Use a minimal set of approved servers and tools. Tool metadata should not be treated as a security authority. Once threat 3, tool poisoning is clear, threat 4, missing human approval becomes much easier to understand. Some operations should never run automatically. Database writes, schema changes, payments, emails, and deletes need explicit review. A secure workflow separates proposal from execution. The agent can prepare a plan, but a human approves the action. This is why the demo uses a proposal-only cleanup tool. Approval is a workflow design choice, not an afterthought. From there, the next practical step is credential pattern for production. The local demo does not need real credentials. If a real system is added later, credentials must be scoped and externalized. Use environment variables or a secret manager. Prefer read-only tokens for read tools. Do not give an agent broad admin access. A credential should match the smallest job the tool performs. This sets up the next important point: what production needs before real databases. Production security is more than one guard function. Use authentication and authorization. Use read-only database roles for read tools. Use parameterized queries or dedicated query APIs. Use audit logs, rate limits, approvals, and alerting. Use sandboxing and network restrictions where possible. Test prompt injection, tool poisoning, and failure paths before launch. Test prompt injection, tool poisoning, and failure paths before launch. That sets up common beginner mistakes. Beginners often expose a tool that is too powerful. They trust the model to make permission decisions. They forget to test blocked paths. They skip audit logs because the demo seems small. They use real-looking data too early. They connect third-party servers without reviewing tool metadata. A safe agent workflow is designed, not hoped for. With common beginner mistakes in mind, the next piece is final demo behavior. The final local demo has two visible behaviors. Safe read requests return fictional demo rows. Destructive-looking requests are blocked before execution. Risky cleanup requests become simulated plans for review. Audit logs show what the tool attempted and what happened. This is the pattern to remember: narrow tools, server-side policy, visible logs, and human review. That idea leads directly to final content recap. MCP security starts with the tools you expose. Do not expose raw database power to an agent. Use narrow tools with clear schemas and explicit effects. Validate inputs on the server side. Convert risky operations into reviewable proposals. Log tool calls and test blocked paths. Before production, add authentication, authorization, least privilege, approvals, and monitoring. That is how you stop AI agents from deleting your databases by design. To wrap up, here is the key takeaway. You now have a structured overview of how to stop AI agents from deleting your databases, MCP security. Review the core ideas, connect them to examples, and revisit concepts like what we are securing, the security roadmap, how MCP tool risk happens when practicing. Subscribe to Easy Machine Learning Guide if you want to learn AI through simple explanations and real industry examples.